reason behind his visit this week is to award him the Bart J. Brock Prize, which Peg is now running up to me with, I see. But okay. And this is a prize that is awarded by the department to a recent PhD graduate based in recognition of their excellence in post-PhD research. And so we actually awarded Nick this prize in, I think, early 2020.
Yeah, that's about right.
And then something else happened. And so we're very glad that he's been able to make the transatlantic trip over to finally receive the prize. So Nick got his PhD here in 2013 and then went on to be a postdoc at Columbia and won an Einstein Fellowship there. And then in 2019 moved to Israel to the Hebrew University. And he's really done a very wide range of research in dynamics and black holes and tidal disruption events and gravitational waves and other things. And what he'll be telling us today about is tidal disruption events. I want to, for example, call out work that he published in Nature recently on offering statistical solutions to the three-body problem. Of course, a classically unsolvable problem, but he managed to figure out some statistical approaches to it that were very compelling. So it really is a great pleasure to welcome him back with this prize, and let's all give Nick a big round of applause.
Oh, thank you so much, Daniel.
So with that, I think we'll go ahead and start the lecture.
Well, thank you so much for the kind introduction, and of course this wonderful prize, which I'm very grateful for. It's always a pleasure to come back to a place that had a really formative influence on your life, and there's no doubt that the CFA was that kind of place for me. This is where I really became an astronomer, so it's wonderful to be back here and to see many familiar faces. It seems that I'm not seeing my screen right here, though, so let me unplug this and replug this. Yeah.
Is it on your screen?
It's visible on my screen. I might need a little help. It's back. All right. Okay. So as Daniel said in his very kind introduction, I'll be talking today about tidal disruption events. I've worked on, I think, a variety of things over my career, but this has been, in some ways, maybe my white whale. Tidal disruption events were the biggest part of my PhD thesis, which I did here with Avi Loeb, and it's a subject that has interested me ever since then. What I'll try to summarize today is the role that tidal disruption events can play in answering some very fundamental astrophysical questions about massive black holes in our universe, and I'll try to present both an optimistic case for what the scientific potential of these transients is, and also an honest assessment of the challenges and what I and my research group have been doing to try and overcome some of the obstacles that exist now between turning TDEs from theoretical curiosities into astronomical workhorses. Now, of course, when making a long journey like a transatlantic flight, you really want to have a good motivation, and while accepting an award was an excellent one, I also have a book to sell you. So if you find anything I discuss in my talk today interesting, I can only recommend that you take a look at the first ever TDE textbook, which I had the privilege to edit and arrange with a handful of other researchers. The individual chapters in the book are collected review articles, so there were many, many authors, some of whom are sitting here in this audience right now. I could ask you to go to Amazon to buy this, but it's very overpriced and I don't get royalties, so really you should just download the individual chapters from the archive, and I think that will be more efficient. Now, before I get into the subject of tidal disruption events, I do want to set the stage a little more by talking about massive black holes in our universe, and as I think probably most people in this audience know, these massive black holes are really ubiquitous in the centers of galaxies, at least above a certain mass threshold. And over the last several decades, we've come to appreciate that these black holes, despite their conceptual complexity, play a very fundamental role in many of the most important astrophysical phenomena in the universe. I could devote an entire talk to this, of course, but just to name a couple, we've seen empirically that there appears to be a very strong degree of coevolution between massive black holes and their host galaxies. And at the larger end of the mass spectrum, it seems that black holes are the objects that are driving this coevolution by providing accretion feedback that fundamentally alters the interstellar medium and the star formation rate in their host galaxy. And I think this is something that, although it has come to be accepted by many people, is still a little bit surprising in the sense that these black holes, despite the massive in their name, are relatively puny objects compared to the galaxies that they inhabit, making up less than 1/1000th of the total mass typically. And the reason that they're able to sculpt and shape their host galaxies is, of course, because accretion onto them releases incredible amounts of energy. And it's that incredible radiative efficiency of accretion disks around black holes, which also leads massive black holes to be the brightest sources of steady electromagnetic radiation in our universe. But despite the centrality of massive black holes to these and many other corners of astrophysics, there are still very fundamental things we don't understand about them, starting with their origins. So observations of very massive high redshift quasars, the black holes in active galactic nuclei at high redshift, really pose a strong challenge for any theoretical model for how you want to make massive black holes in a limited amount of time. And as a result of this, there are many different competing theories for how you can assemble high mass seeds of black holes in the early universe, and we don't know which of these theories is correct, or maybe if any of them are correct. To some degree, this is a solvable question if we could go out and measure the distribution of very low mass, some would say intermediate mass black holes that exist today in the present universe in the centers of dwarf galaxies. These low mass black holes, if they have not grown significantly over cosmic time, represent a kind of fossil record that would tell us about the currently unknown formation mechanism for supermassive black holes at high redshift. Likewise, there are major uncertainties in the evolution growth history of massive black holes in galactic nuclei. And again, this is something that in principle is an empirically solvable question if we had a way to measure the spins of massive black holes at low redshift, because the spin distribution is really what encodes the most salient details of their growth history. But in practice, these are very hard empirical questions to tackle. To give a little more motivation for why we should be interested in them, I'm going to show a couple of plots from various review articles. So here is a collection of mass distributions, so essentially histograms of black hole seeds of different masses for 3 different massive black hole formation scenarios in the early universe. The details don't matter too much. Here we have something involving POP3 stars. Here we have something involving runaway collisions in very dense star clusters. And here we have direct collapse of very low metallicity gaseous mini-halos. But what I think you can see from these histograms is that different formation scenarios predict very different distributions of black hole masses. And so if we could go out today and measure all of the masses of black holes in dwarf galaxies, and we found a huge number of very low mass objects, that would suggest that it would be one of these low mass seed formation scenarios that played a very important role in the formation of black holes in the early universe. Likewise, if we want to think about what we can learn from spin distributions, this is a very complicated plot, and you shouldn't pay attention to individual panels, but each of these panels is a histogram of different black hole spins at different bins of redshift. So the different rows are different bins of redshift. The columns represent different values of the dimensionless black hole spin, a number that ranges from 0 to 1. And essentially, each of the different columns represents some different theoretical scenario for how massive black holes accrete or otherwise acquire mass over cosmic time. And hopefully what you can see from comparing really random panels to each other is that different growth scenarios predict very different distributions of present-day black hole spin. Some are very bottom-heavy with all the spins piled up at 0. Some are very top-heavy with the spins all piled up at 1. And so if we could really get a handle on the spin distribution of massive black holes in our universe, we could understand which of these scenarios is correct. The problem for all of these lofty goals is that there are very few techniques that allow us to robustly measure large samples of black hole mass and spin, especially once you go outside the local universe. And this is where we get to the subject of this talk, because this is where I think tidal disruption events, or TDEs, as is the acronym I will slip into for the remainder of this talk, can potentially bring something very new and valuable to the table. So a tidal disruption event is depicted here in cartoon form in this classic paper by Martin Rees. You have a supermassive black hole in the center of a galaxy. You have this tidal disruption radius around it. It's a few tens of Schwarzschild radii. And then you have an unlucky star approaching on a very parabolic orbit. The star has been scattered onto this orbit, and once it starts to graze or enter the tidal disruption radius, it's torn apart and spaghettified into these elongated debris streams. Now, tidal disruption events are potentially very appealing probes of black hole demographics for a variety of reasons. One is that they can occur in every galaxy that hosts a massive black hole, making them an unbiased, or at least differently biased, tracer of black hole demographics than many of the existing techniques that we use. Second, they're extremely high luminosity transients with peak optical, UV, and X-ray luminosities that get above 10 to the 44, sometimes even 10 to the 45 ergs per second. And this means that they can be seen to cosmological distances. So this is doing a lot better than black hole mass measurement techniques, for example, like unresolved stellar kinematics that only work in the local universe. And finally, TDEs, the complicated sequence of events that is set into motion by the disruption of the star is in principle something that is governed by relatively few free parameters, meaning that if you have a theoretical understanding of how TDEs work, parameter estimation is in principle a solvable problem, and you can take observables like spectra and light curves and back out key parameters of interest. And of course, in this talk, I've really focused on these, but there are properties of stars and the orbit that may be of interest for other applications as well. There are other motivations that I could spend a long time talking about, but I'll just address very briefly in a single sentence each. If you learn something about the volumetric event rate of TDEs, you can learn something about stellar dynamics and stellar populations on sub-parsec scales in galactic nuclei. This is a question that may seem academic, but has broad implications, for example, for gravitational wave astronomy and populations of gravitational wave sources. Second, a variety of recent discoveries by the IceCube array has determined that there may be a statistically significant association between TDE flares and high-energy PeV level neutrino emission, suggesting, although this is still somewhat controversial, that TDEs may be a significant contributor to the background of high-energy neutrinos in our universe. Other suggestions have been made about TDEs and ultra-high-energy cosmic rays, which to some degree parallel this, although there's less evidence for that. Finally, there are a variety of questions in fundamental physics which can be tackled by TDEs. One that I think is very elegant, but which I don't have time to discuss here, is the weak cosmic censorship conjecture. Another, which I'll touch on at the end of this talk, is using tidal disruption flares to obtain novel constraints on the existence of ultralight bosons in our universe, although that will really be a side application. So, okay, TDEs in principle seem like great probes of black hole demographics. But why haven't they solved these big questions that I posed at the beginning of the talk yet? One reason they haven't is that our current sample, although growing, is still relatively limited. In this plot, which is from a review article by Suvi Ghazari and is now a few years out of date, you can see that we've discovered something on the order of 50 strong TDE candidates. The discovery of these TDEs dates back to the 1990s when they were found in wide-field soft X-ray surveys like ROSAT. In recent years, the rate of discovery has really been dominated by wide-field optical surveys, which detect lower energy but still very luminous emission. And over my career, at least, TDEs have really gone from theoretical curiosities to something that is observed in larger and larger numbers. But as impressive as this rate of growth has been, the rate of TDE discovery is going to explode over the next few years, and I'll explain what I mean about that. But first I want to review the different kinds of emission that are seen observationally in TDEs. So a non-trivial subset of TDEs exhibit strong soft X-ray emission, which usually, although not always, is quasi-thermal in nature. So the luminosities of this usually quasi-thermal X-ray emission range from maybe 10 to the 42 up to a few times 10 to the 44, or in extreme cases 10 to the 45 ergs per second. If you try to fit this thermal emission with a single temperature blackbody, you get a blackbody radius that's comparable to the event horizon of the massive black hole, and you get a blackbody temperature on the order of 0.1 kiloelectron volts. This set of very high-level descriptions of TDE emission is consistent with the simplest kind of accretion disk model that you can create, a multi-temperature blackbody akin to a Shakura-Sunyaev disk that orbits the supermassive or intermediate mass black hole at relatively small scales. So in that sense, X-ray emission from TDEs often resembles a sort of scaled-up version of an X-ray binary in a soft quasi-thermal state. TDEs that emit significant amounts of soft X-ray emission are in some sense a supersized soft-state XRB. Historically, these have been found by a variety of different X-ray surveys, Presently, the survey with the greatest potential to find them is eROSITA. So what's shown right here is the main eROSITA TDE paper. This is a snapshot of 13 different X-ray spectra from TDEs found on the Russian side of eROSITA. eROSITA, of course, has been shut down for geopolitical reasons beyond the control of astronomers, but if it turns back on in the future, it's very likely to discover something on the order of 50 new tidal disruption events during each subsequent year of observation. But as I alluded to earlier, the present-day rate of TDE discovery is really dominated by optical surveys, which observe a very different kind of emission. So the optical and near UV emission seen in most TDEs that are found today reflects a different kind of quasi-thermal photosphere. The luminosity of this thermal photosphere is similar to what we saw in the X-rays, but the blackbody radius is something like 3 orders of magnitude bigger, and the fitted blackbody temperature is 1 to 2 orders of magnitude smaller. Here we can see examples of bolometric light curves, fitted blackbody radii, and fitted blackbody temperatures as functions of time for a sample of 17 of these flares found by the ZTF survey. And what's really notable here is that this kind of emission, unlike what we see in the X-rays, is totally inconsistent with a simple, naive, compact accretion disk model. So what's going on here is that something is creating an optical and UV photosphere that's on the order of, well, about 2 orders of magnitude bigger than the tidal disruption radius, which is the naive size you would expect for some sort of accretion disk. And I really need to emphasize something that will be a major theme of this talk, which is that even though most TDEs today are found from their optical and UV emission, we do not understand, even at a qualitative level, what is the power source for this emission and what is the geometry of the photosphere that is producing it. Okay, so I promised a second ago I would describe what the future portends, and over the course of the next few years, our sample of TDEs is going to grow by probably something around 2 orders of magnitude. One reason for that is the LSST survey. So just taking what we know empirically about TDEs found by other optical surveys, it is reasonable to expect that LSST will find between 3,000 and 8,000 new tidal disruption events every year. But of course, discovery is not the same as secure identification, and if we use classic semi-empirical criteria to distinguish TDEs, which are a relatively rare type of transient, from their much more numerous imposters, such as nuclear supernovae and AGN variability, these kinds of semi-empirical criteria are only going to be capable of securely identifying less than 10%, maybe as low as a few percent, of the total number of TDEs that will be found by LSST every year. This is not a very high efficiency factor, and it's a little disappointing. There are, in principle, a number of things you can do to increase your yield. One would be to not rely on semi-empirical identification criteria, but instead to rely on predictive deterministic models. The problem is that these don't exist yet. Another thing you could do is try to get more secure identifications from spectroscopic follow-up, but of course, obtaining that kind of expensive follow-up for thousands of flares every year is unlikely to be practical. A different option, which I'll elaborate on in a moment, which I think may be the most promising, is multi-wavelength follow-up with other wide-field surveys. And in particular, this is where a new mission based out of Israel that I've been privileged to work on enters the picture. So ULTRASAT, which is an upcoming Israeli-led wide-field UV survey satellite, is potentially going to be even more exciting and more useful for TDE discovery than LSST will be. So this is Israel's first really serious space-based astronomy mission. It's a mission led by various Israeli agencies and corporations, but with significant contributions from DESI in Germany, and NASA recently bought in the United States. Its present launch date is early in 2025. It is a single band survey. It has a single near ultraviolet band, an enormous field of view, respectable limiting magnitude, and is in many ways the ideal survey instrument for finding bright and blue transients such as tidal disruption events. There are a number of other goals as well, from supernova shock breakout to finding kilonovae that are counterparts to gravitational wave signals, but today I'll just be focused on the TDEs. One way to really see the incredible discovery potential of ULTRASAT is by looking at its GRASP, a measure of the effective volume per unit time over which any kind of wide field survey is capable of discovering transients. So here I have a plot of GRASP versus observational wavelength for a variety of different wide field surveys, both existing ones and near future ones. And you can see that ULTRASAT, and along with LSST, are really in a league of their own, with GRASPs, at least for relatively hot sources, that exceed all previous surveys by at least 1 order of magnitude. Now, as far as TDs go explicitly, one of my jobs as the co-chair of the TD working group in ULTRASAT is to figure out what is the optimal survey strategy for maximizing our discovery yield, and also figuring out what sorts of event rates and parameters we can really predict. And I won't belabor all of the details here, but you can see some simple predictions in these two plots right here. So both of these plots show an expected rate of total number of detections in a year of ULTRASAT observations. This is shown as a function of redshift, and these are cumulative plots. So this is the number of detections within a certain redshift. ULTRASAT is currently expecting to have two different survey modes. One is a high cadence, low area mode of operation, where it will stare at a single patch of the sky for a long period of time to find fast and faint transients like supernova shock breakout. This is not the optimal discovery mode for looking for TDs. Instead, most TDs will be found from a low cadence survey, which tiles an order unity fraction of the sky with a cadence of 3 days. Depending on what you assume about the redshift evolution of TD rates, this will find somewhere between 1,000 TDs every year up to 10,000 TDs every year. So ULTRASAT is really going to do an incredible job at expanding our sample of TDs. The scientific potential of TDs to measure black hole demographics, both from ULTRASAT and LSST, and indeed the expected synergy between them, is going to be incredible. But this is where we run into theoretical problems. And in particular, the really fundamental problem is that we don't understand the time evolution of tidal disruption events. And the reason for this is that they are very hard to simulate in a first principles way. There are parts of the TDE problem that are well understood. For example, the disruption of the star itself as it passes too close to the supermassive black hole is something that can be modeled pretty accurately analytically, and it's also something that a wide variety of numericists have simulated in a first principles way, and these simulations are relatively well converged. But after the disruption of the star, everything else gets pretty complicated, and there are a couple of major questions which I really want to emphasize that will motivate the rest of this talk. So one of these questions is, how does the spaghettified debris, these streams of stellar leftovers that fly away from the black hole with eccentricities greater than 0.99, how does this stellar debris actually dissipate its orbital energy to circularize into something like an accretion disk? The second question, which is downstream from the first one, has to do with the unknown origin of the optical and UV emission, which is going to power increased rates of TD detection over the next 5 years. So here, we can't even agree on the underlying power source for the optical UV photosphere. In some theoretical models, this is a shock-powered photosphere. In others, this is essentially a reprocessing layer that veils an underlying central engine and accretion flow at small radii. Beyond the power source, we have no idea, in a theoretical sense, what is the geometry of this photosphere. There are a number of other important questions also. Some that I find very compelling involve the unknown event rate of TDs and the apparently low jet launching fraction in TDs, but you'll have to ask me later if you're curious about these. So the fundamental reason that this is a hard problem theoretically, and the reason that I'm posing a lot of questions rather than a lot of answers, is the large dynamic range involved in simulating a TD from first principles. So after the star is disrupted, the spaghettified debris streams have typical widths that are of order 1 Schwarzschild radius. They have a pericenter that's of order 10 Schwarzschild radii, and they have apocenters that are between thousands to 10,000 Schwarzschild radii. The result of this is that if you want to simulate the long-term evolution of a TDE, you're looking at a simulation box which is 99% empty by volume. And this is a very challenging problem that is almost impossible for any kind of static grid code to approach in a computationally efficient way. At first, this seems like it is a very well-suited problem for a finite mass hydrodynamics scheme like SPH. And indeed, simulating a TD was one of the first use cases that motivated the development of SPH in the late 1970s and early 80s. Here you can see a quite impressive simulation using only 500 SPH particles. Given that resolution, it's actually kind of amazing how much it got right. But in practice, there are a couple of subtle challenges that make this problem very difficult for any finite mass scheme to really tackle successfully. Additional challenges enter the picture when you consider non-hydrodynamic pieces of physics that are needed to understand the evolution of a tidal disruption event. General relativistic precession may be very important for the circularization of the stellar debris. So one leading theory is that relativistic apsidal precession causes an outgoing debris stream to intersect with an incoming debris stream, dissipating their orbital kinetic energy in a shock and driving the formation of an accretion flow. So in principle, you may need some treatment of GR if you want to get this problem simulated correctly. Once circularization begins, very quickly, the fluid becomes dominated by radiation pressure, so maybe you need a dynamical treatment of radiation transport. This is astrophysics, so of course you can never rule out that magnetic fields are important, but in practice, the limited number of TD simulations done involving magnetohydrodynamics suggests that magnetic fields are not terribly important for early stages of circularization. The end result of all of these challenges is that a astrophysically typical TD has never been simulated from first principles, even in pure hydrodynamics. And the way that theorists have tackled this problem is by taking a lot of unphysical, or maybe it would be more accurate to say unastrophysical shortcuts. What I mean by this is illustrated in the collage I've assembled on this page right here. So here, we're looking at 4 different snapshots from 4 different long-term evolution simulations of tidal disruption events. And all of these simulations have had to find some way to cheat in order to make the problem computationally tractable. In the family of simulations represented by this early work I did during my PhD here, we cheated by taking a main sequence star and a supermassive black hole, but instead of putting the star on a realistic parabolic orbit, we put it on a pretty unrealistic low eccentricity orbit to artificially reduce the dynamic range. What's seen in this kind of simulation is fast circularization. Another popular approach is to take a main sequence star on a realistic parabolic orbit, but to simulate its disruption by a relatively uncommon, very low mass, intermediate mass black hole, something on the order of 1,000 solar masses. What's seen in this family of approaches is generally very slow circularization. In recent years, there's been a kind of clever approach pioneered by Clement Bonnereau and Wenbin Liu, where realistic parameters are used, but they cut out the computationally challenging evolution of the debris streams themselves. They assume that they know from first principles exactly how the debris streams will self-intersect and inject mass into the system, so they put in a source term of mass and momentum to represent the evolution of the debris streams. As I will show later in this talk, this approach is not going to be valid for very long. And then a final approach that's used is sometimes just to skip ahead to the end result of circularization and begin with axisymmetric initial conditions that describe a fully circularized accretion disk. We can learn some things from this approach, but obviously it's skipping one of the most important parts of the TDE problem. The main takeaway I hope that everyone gets from this collage is that even if you had never heard of TDEs in your life before stepping in here, none of these simulation approaches give anything that appears converged with the other ones. Even at a qualitative level by eye, these all look totally different from each other, and quantitative comparisons are also completely different. So in the absence of predictive models or first principle simulations, we haven't really given up, and there have been a variety of very ambitious approaches to try and measure TDE parameters, such as black hole mass, from observed light curves. And in general, these approaches wind up taking something that we understand reasonably well, such as the dynamical mass fallback rate dmdt, which is produced in the aftermath of tidal disruption and kind of freezes in as a fixed part of the problem, and then combining this with relatively strong assumptions about the evolution and geometry of the photosphere. This approach is most popularly used in a code called MOSFET, which was motivated by the reprocessing picture of TDE emission. There's also a different approach motivated by the shock paradigm for optical UV emission. What both of these approaches have in common is that they do have to make very strong and not necessarily correct assumptions about the time evolution and the geometry of the optical UV photosphere. And ideally, we would really like to test these assumptions and see if they're correct using first principles simulations. Now, I think I've finished about the first half of my talk, and in the second half, now that I've laid out this problem, I want to give some reasons for optimism. So in the second half of this talk, I'm going to overview work done mainly by my collaborators, which I think points the way forward to actually extracting black hole parameters of interest from TD observations, despite the very difficult problem of simulating these from first principles. And I think one probably viable path forward is to apply novel hydrodynamics algorithms to actually tackle this problem in an ab initio way. And I'll show some results that represent first steps towards doing this. The second approach is to take different subsets of TD observations where we think that what's going on can be represented with simpler and usually semi-analytic kinds of models. And so parameter estimation can be done with a greater degree of theoretical confidence that we understand what exactly we're putting into the model and how that correlates to different kinds of observables that we're looking at. So the particular example of this that I'll focus on in this talk is looking at the quasi-thermal soft X-ray emission, which almost certainly is coming from some quasi-circular inner accretion flow. So as far as I'm aware, there's never been an alternate proposal for where the quasi-thermal soft X-ray emission in TDEs is coming from, even if the bulk of the debris in a tidal disruption event does not circularize or takes forever to circularize. There is some amount of material that increases its binding energy by multiple orders of magnitude and gets right down to the bottom of the potential well of the supermassive black hole outside the event horizon. And traditionally, this kind of emission has been fruitfully modeled in many different kinds of accreting black hole systems with semi-analytic accretion disk models. At later times, there may also be some hope for applying traditional accretion disk models. If you look at TDEs 5 to 10 years after the peak of the optical flare, many observed TDEs remain bright in far ultraviolet wavelengths with slowly evolving FUV luminosities that can be well fit by a fully circularized, viscously spreading accretion disk model. I won't have time to get into this approach here, but ask me about it later if you're curious. So to begin with, I want to share some recent simulations led by Zach Andelman, done with a novel GRMHD code developed by Matthew Liska and Sasha Tchaikovskoy, which we performed over the last couple of years and which were published last year in 2022. So the code that we used is Hammer. This is a GPU-accelerated version of the widely used GRMHD code HARM. By operating with adaptive mesh refinement and running on GPUs, even though it is a static grid code, it is more able to tackle the problem of a tidal disruption event from first principles. So what we're seeing in these movies is the return of debris streams to pericenter. Sometimes these debris streams make it through pericenter and self-intersect due to relativistic apsidal precession, but as time goes on and more material circularizes into some kind of messy accretion flow at small radii, the streams are less and less successful at making it through pericenter because they dissipate more and more of their energy via shear and shock interfaces between the returning debris streams and the quasi-circularized accretion flow that's forming at small radii. So what we learned from this simulation is that debris circularization can be a kind of runaway process. For the parameters that we've picked here, a realistic star, a realistic orbit, a realistic supermassive black hole, but a fairly small pericenter so that GR precession is important, we see runaway circularization of the debris. The circularization of a little bit of gas creates tightly bound material in some sort of elliptical accretion flow. That elliptical accretion flow becomes very efficient at dissipating debris energy in this shear interface layer and the shocks that form there. This circularizes more material, which leads to even more efficient dissipation, and the process begins to run away. Now, even though this was done with a really state-of-the-art GPU-accelerated GR hydro code, we did not include MHD in this simulation, I should say that up front, we were only able to simulate that the long-term evolution of this TDE, long-term is in quotes, for the first 6 days after the onset of mass return. So even throwing this very sophisticated novel numerical code at the problem, and even though we learned very interesting new things about the evolution of TDEs, we still have this fundamental computational challenge we're fighting against if we want to study the long-term evolution of these systems. And I should emphasize for anyone who did not pay very close attention to an early slide that observed TDE light curves rise and fall on timescales that are much longer than 6 days. Typical rise times are on the order of weeks, decay times are weeks to months. So only getting 6 days is really not going to cut it in the long run for making predictive models for what these flares do. Nevertheless, I think we have learned a lot from this really first example of an ab initio simulation of a tidal disruption event. The main thing that we see is that between episodic shocks forming at the stream self-intersection radius and continuously growing shocks formed at this shear interface layer between returning streams and the nascent accretion disk, runaway circularization is a feature of what's going on. So here, what I'm showing you is a snapshot in time at the end of the simulation, 6 days after the beginning of mass return. The different curves are streamlines of fluid motion. The pericenter of the debris is right here. And the colors correspond to the mean eccentricity of fluid along these streamlines. So we've seen that in the first 6 days after the beginning of mass return, we've gone from debris streams with eccentricities of 0.99 to debris that has eccentricities of 0.9, 0.7, even 0.5 at small radii. This suggests that for relativistic pericenters, it does not take that long to create a quasi-circular inner accretion flow. This quasi-circular inner accretion flow is subsumed by an expanding outflow. So the circularization process in this simulation is also very efficient at unbinding a lot of the material from the disrupted star. And this expanding outflow is almost certainly going to absorb any photons emitted either from the accretion process or from shocks that are driving debris circularization. So everything that's happening in this simulation is going to be shielded behind a reprocessing layer of outflowing material. Okay, so even throwing the state-of-the-art GR hydrocode at the problem, if this only got us 6 days into the problem, what can we do? This motivated me to work with my colleague at the Hebrew University, Elad Steinberg, to tackle the problem of TDE simulation with a totally different kind of numerical algorithm, which I'm going to show you here. So here, we've again chosen a main sequence star, a realistic orbit, a 10 to the 6 solar mass black hole, but now our pericenter is not so relativistic. It's at 50 gravitational radii instead of 7, which was the previous simulation. What you're seeing in this movie is a look at the tidally disrupting star in its non-inertial frame of reference. So our simulation box is tracking the stellar center of mass. The arrow points to the supermassive black hole. By this point in time, the star has already been spaghettified into this long and loosely bound debris stream. It's flying out to an apocenter of about 10,000 Schwarzschild radii. Once it reaches that apocenter, the most tightly bound material is going to turn around and start coming back to the supermassive black hole to begin the process of debris circularization. Once this happens, we're going to switch to the lab frame of the supermassive black hole, and we'll see what unfolds. One important thing to realize here is that since the pericenter we've chosen is so non-relativistic, this hydrodynamic simulation is not really expected to see significant dissipation of orbital energy in self-intersection shocks. The amount of relativistic apsidal precession is orders of magnitude smaller, measured in radians, than what was in the previous simulation. But what we see instead is that there's a kind of compression shock at the pericentric nozzle. So returning debris streams dissipate energy in a converging fluid flow at pericenter. This dissipation of energy, and I'll go back 1 minute so you can see this again, leads to inefficient circularization. But even though the circularization is initially inefficient, it's beginning to create, it at first slowly and then quickly fills in this Keplerian ellipse with a layer of partially circularized debris. And what we see once again, even though we're using a totally different algorithm and somewhat different stellar parameters, is runaway circularization. As soon as you start producing a partially circularized accretion flow, shear interface layers and shocks between returning debris streams and this partially circularized flow lead to the same runaway circularization phenomenology that we saw earlier. And that's exactly what happens here, except that in this simulation, we've gone 65 days into the tidal disruption event up to the typical peak of the optical UV light curve. So after doing this radiation hydrodynamics simulation, we post-process the results to estimate synthetic spectra seen from different viewing angles. We feed these synthetic spectra into synthetic observations. So we take the different wavebands of the Swift UV-OT telescope and the ZTF optical survey, and we use these synthetic multiband observations to fit single temperature black bodies at different moments in time and from different viewing angles, the same way real observers would. And by doing this, we can make histograms like this. This is a histogram of peak luminosity seen in our simulation. The reason it's a histogram is different viewing angles would fit different peak blackbody luminosities. If you look at this range of peak blackbody luminosities and you compare it to the actual peak blackbody luminosities from a sample of real TDEs, you see that we're in the right ballpark. Our simulation is producing peak blackbody luminosities that are compatible with the higher end of real observed TDEs in the universe. You can do the same kind of exercise for fitted blackbody radii. Again, we find synthetic fitted blackbody radii, which are comparable to the larger blackbody radii that are fitted by real observers looking at real TDEs. Again, you can do the same thing with blackbody temperatures. Here there's actually a somewhat wider spread. This depends a little more on viewing angle than the other two parameters. But ultimately what we see is, again, very consistent with observations. Now, the reason that we were able to actually simulate this ab initio TDE for an order of magnitude longer than anyone else has been able to is that we were the first people to use a moving mesh radiation hydrodynamics algorithm. So my colleague Elad Steinberg is a brilliant numericist who developed his own moving mesh hydrodynamics solver, Rich, during his PhD thesis. For those in the audience here, Rich is very similar to a repo. It has a flux-limited radiation transfer module that was added later, and it is the good match between the strengths of moving mesh hydrodynamics and the challenges of the TDE problem that really make this the perfect kind of hydrodynamics algorithm for finally solving this problem and making deterministic predictions that map parameters of interest to observables like blackbody luminosity and blackbody temperature. I won't belabor all of the details here since time is running a little low, but the main thing I'll point out is that in this simulation, circularization is initially quite inefficient because it's being driven by these weak compression shocks at pericenter. It only becomes efficient later on, within about a week of peak light, once you get this runaway circularization between incoming debris streams and the eccentricity of 0.8 or 0.9 accretion flow that is formed. At peak light, the primary power source is shocks, but the runaway circularization process suggests that not too long after peak light, accretion power is probably going to overtake shock power in driving the total luminosity from this flare. And even though this pilot study is really a first principle simulation of only one set of parameters for a tidal disruption event, we have 12 million CPU hours with our collaborator Elena Rossi in Leiden Observatory, so we're hoping to expand this into a real parameter study over the next year. Okay, in my last few minutes, I want to step back from this theoretical problem of simulating TDEs from first principles and focus on a more observational problem of asking, even without a first principles understanding of the entire TDE problem, what can we glean from existing observations with existing theoretical models? And here, I think one of the best avenues to make progress is through the X-ray continuum fitting approach. So the reason that this works is that in most TDEs with strong soft X-ray emission, the X-rays that we see are very thermal, analogous to the high soft state of an X-ray binary. And for anyone here who has listened to talks from Ramesh Narayan and his research group, you know that when you have something like a soft state X-ray binary, you're able to fit semi-analytic disk models, so general relativistic versions of the usual Shakura-Sunyaev accretion solution that are then processed through some sort of ray tracing code in order to fit the underlying parameters of interest in this accretion flow. So this continuum fitting technique is widely used in the study of X-ray binaries. Historically, it has not been applied very widely to supermassive black holes for the reason that supermassive black hole disks, namely AGN, generally have many more emission components that often dominate the soft quasi-thermal component. AGN also typically exists in dusty environments, which creates its own challenge, but TDs are really a sort of optimal use case for continuum fitting in the realm of intermediate and supermassive black holes. My efforts in this have really been led by this fantastic postdoc, Xixiang Wen, who was formerly at the University of Arizona with Ann Zabladoff. Now he's at Nijmegen with Peter Jonker. And what we've developed together, the four of us, is a publicly available code that can be put into XSpec in order to perform X-ray continuum fitting on multi-epoch TDE X-ray spectra. So the basic assumptions that go into this, we use general relativistic semi-analytic models. We ray trace null geodesics through a Kerr spacetime. We consider the emission to be a lightly Comptonized multicolor blackbody. These are the reasonable assumptions. The somewhat more questionable assumptions, which I'll put on the table right now, are that these accretion disks reside in the equatorial plane of the massive black hole. They're axisymmetric, meaning fully circularized, and at super Eddington epochs, they can be well characterized by slim accretion disk solutions. So I think reasonable people could take issues with all of these assumptions. We're working to generalize them right now. In general, though, what I will say is that all of these assumptions should become true at late enough times in any tidal disruption event. And the question that we don't know the answer to right now is, what is a late enough time? So what I'm going to show you now, I think you should take with a little bit of a grain of salt, but it's meant to show the fundamental promise of X-ray continuum fitting, perhaps with future bells and whistles that will come from generalizing these assumptions. So to begin with, let's look at a couple of very well-studied tidal disruption events around supermassive black holes. Here's one called Assassin 15OI, where we have two high-quality epochs of XMM Newton observations. What you can see here are the contours in the dual parameter space of black hole mass and dimensionless black hole spin for different confidence limits. So blue you can think of as essentially a 1 sigma error region. Purple you can think of as a 2 sigma error region. What you can see here is that while we get interesting constraints on the mass of the underlying black hole, the spin is totally unconstrained. And the reason for that is that when you do this kind of X-ray continuum fitting exercise on a single epoch or two epochs that are closely spaced in time, you don't have very much lever arm in the observations to constrain the black hole spin. there's a strong degeneracy between black hole spin and accretion rate through the disk. And you really need multi-epoch observations that sample very different accretion rates in order to break this degeneracy. So an example of this is an even better studied TDE, Assassin 14Li. Here, we have 10 publicly available XMM Newton epochs of observation, and what you can see is that both in terms of mass and spin, the 1 sigma and 2 sigma constraints on this plane become much tighter. You get a very narrow banana, and the joint constraint, even though it spans a significant range in both spin and mass, is very narrow indeed. So I think what the takeaway from this figure should be is that X-ray continuum fitting has a lot of promise to really pin down parameters of interest, especially if it can be paired with another technique that gets you one of these and breaks the mass spin degeneracy in this banana. But actually taking advantage of X-ray continuum fitting requires a lot of expensive multi-epoch X-ray observations. It's not necessarily a cheap exercise. However, one other application of this, which I think is even more exciting, is looking at a very unusual TDE candidate first discovered by Da-Cheng Lin in 2018. So this is a multi-year X-ray flare discovered in this tiny companion to a nearby lenticular galaxy. Depending on your point of view or what side of the bed you woke up on this morning, this host object is either a tidally stripped dwarf galaxy or a very overweight globular cluster. It appears to have a mass of about 10 to the 7 solar masses and an effective radius of about 25 parsecs. In the discovery paper by Da-Cheng Lin, this quasi-thermal multi-epoch X-ray spectrum was fit with relatively simple accretion disk models, and what Da-Cheng found was that the best fit mass puts the underlying TDE firmly in the elusive mass range of intermediate mass black holes. So once Peter and Wen and Ann and I saw this, we got very excited and decided to apply our own, I think, somewhat more sophisticated TDE models to this continuum fitting problem. One notable uncertainty, which I should mention up front, is that we don't know for sure the redshift of the host. This object is so faint that even with a Magellan spectrum, we were unable to obtain actual emission lines that would let us ascertain the redshift of the host. The chance coincidence probability is relatively low, so we are fairly confident that this host object has the same redshift as the massive lenticular galaxy, but it's not something that has been rigorously demonstrated yet. So this is a notable uncertainty that I'll admit right now. So what we did was we took 5 epochs of high-quality X-ray spectra and applied the same continuum fitting procedure that I described earlier to them. In our fiducial model, where we assume that the redshift of the true host is adjacent to the redshift of the lenticular galaxy, we get an incredibly tight constraint in the parameter space of black hole mass and black hole spin. So we confirm Da-Cheng's assessment that this is really an intermediate mass black hole on the order of 10 to the 4 solar masses, a factor of a few smaller than his estimate, but very much an intermediate mass black hole. And although I'm a little biased, I would say that I think this is one of the strongest IMBH candidates known in the literature to date. It's also, as far as I'm aware, the first IMBH candidate ever to have a spin measurement, although, again, I will note that the spin measurement comes with a significant uncertainty. So in the right panel, we do the same exercise, but we allow the redshift of the host to float as a free parameter that we fit for. And if we allow the host redshift to float, the mass constraint remains. It's still an IMBH, but the spin constraint goes away. So you should take this spin constraint with a grain of salt, but if our educated guess is correct, that it's at the same redshift as the lenticular galaxy, which is something that ultimately can be tested in the future with further spectroscopy, then I think this really is the first spin measurement of an IMBH. One very interesting thing about this is that it opens the door to new tests of fundamental, or at least astroparticle physics, via superradiant scattering instabilities. I'm going to go a little quickly over this, but the very short version of this story, which dates back to the 1970s, is that if ultralight bosons exist in the universe, rapidly spinning Kerr black holes become unstable to catastrophic de-spinning through runaway boson production. The basic idea here is that if you have an ultralight boson whose Compton wavelength is at the same order of magnitude as the physical size of the event horizon of a black hole, the spin kinetic energy of that black hole is going to be converted into rest mass energy of a giant bound cloud of bosons. And this can happen over astrophysically interesting timescales. In this sense, every measurement of a rapid spin for an astrophysical black hole rules out between 1 to 2 orders of magnitude in mass space for putative ultralight scalar or vector bosons. An example of this can be seen in this beautiful figure from Vitor Cardoso. So in this figure, we have black hole mass, we have black hole spin. The individual data points are existing mass and spin measurements, both with electromagnetic techniques in black and gravitational waves in red. What we see here is that these existing mass and spin measurements rule out significant chunks of mass in the space of putative ultralight scalar bosons. So the colored contours represent boson masses, 10 to the minus 14 eV, 10 to the minus 13 eV, etc., that would be ruled out if they overlap with a spin measurement of an astrophysical black hole. And what you can see from this figure is that by measuring the spins of stellar mass black holes, we rule out one mass range of possible ultralight bosons. By measuring the spins of supermassive black holes, we rule out a different mass range of ultralight bosons, but there's a real gap in the middle. And if our guess about the redshift of J2150 is correct, the measurement of the spin in this TD is a way to fill in the gap and rule out entirely new masses of ultralight bosons in the universe. Okay, to wrap everything up, hopefully I've convinced you that over the next few years, our sample of tidal disruption events is going to expand by at least 1 and probably 2 orders of magnitude, and that this enormous near-future statistical sample carries with it a lot of scientific potential for answering fundamental questions about the demographics and maybe even the origins and evolution of massive black holes in the universe. And a lot of the reason for this stems from the relatively small number of free parameters that in principle make TDEs a solvable problem. They're not a solved problem because they are very, very hard to simulate from first principles. But what I've increasingly been convinced by, and what may be of interest to some theorists in the audience here, is that by applying modern moving mesh algorithms, it really is possible to simulate typical and astrophysically realistic TDEs from disruption at least up to the peak of their light curve, making it possible to finally have deterministic predictive models for emission from tidal disruption events, which, if they can be expanded across parameter space in the next few years, would enable actual parameter estimation from this VRO and ULTRASAT sample of optical UV light curves. These first examples of ab initio simulations that I showed you indicate that a lot of the existing questions don't have simple answers, and whether or not tidal disruption debris circularizes quickly, whether or not peak luminosity is shock-powered or accretion-powered, is ultimately something that is going to come down to a case-by-case basis, depending on where you are in the parameter space of black hole mass and how relativistic your pericenter is. So there's not necessarily a single answer to these questions about TDE physics, but there are answers, even though they depend on the underlying parameters. In both cases, in both of the ab initio simulations I showed you, we did see one very interesting and novel thing, which is that no matter how circularization begins, once it passes some point of no return, it really does eventually become a runaway process that is dominated by shock dissipation between returning streams and a partially circularized inner accretion flow. This appears to be a relatively robust conclusion, although of course it would be very nice to generalize it with simulations of other realistic TDEs. Finally, I think this really exceptional TDE candidate, J2150, shows both the promises and the challenges of X-ray continuum fitting, and I think more generally demonstrates that TDEs offer a relatively novel and very valuable probe of intermediate mass black holes in our universe, which have remained elusive to more traditional discovery techniques. So with that, I think I'll wrap up now. Thank you very much for listening and for the invitation back home.
Before we get to questions, let me mention that we do have a couple spots remaining for dinner tonight. So if you're interested in that, please find me after the talk.
Okay, I have a question about something that you didn't talk about much, the optical spectra.
Mm-hmm.
So, from what I remember, there were papers claiming that the signature TDEs would be highly variable coronal lines, and like ionization. And these lines, they actually form in very narrow forms of parameters, like density and temperatures. So, don't you think that if you get good enough spectra with good enough spectral resolution to resolve the line shape, you can actually try to work back the photospheric layer, like the shape of the emitting photosphere, because it's actually like these are very unique lines, which are like in the small density ranges, like 10 to a few.
Okay, so that's a good question. What I know about coronal lines in TDs does not come so much from what you could call the prompt emission, but rather from recombination echoes. So what has definitely been seen in a variety of TD follow-up observations on the order of 10 years after the discovery of different flares is that high ionization coronal lines start to turn on in the host galaxy. So this appears to be some kind of recombination echo moving outwards through the interstellar medium in the galactic nucleus. Stephanie Camosa has been the main person, I think, doing work on this. As far as the prompt emission goes, it is true that there is a pretty rich variety of emission line spectra that are seen in observed TDs, and some of these spectra do reveal high ionization components. One of the things that is studied the most at present is the existence of so-called Bowen fluorescence features. So these Bowen fluorescence features are generally excited by some sort of high energy ionizing continuum, probably in the extreme ultraviolet. I have not worked on them myself, but when I talk to radiation transfer experts and ask them the question that you asked me, what they tell me is, unfortunately, that it's a very hard problem, and that just by looking at the Bowen fluorescence luminosity, there are a lot of degeneracies between the underlying unobservable extreme UV luminosity and the photosphere geometry, and it's hard to decisively pin down one or the other. Here I'm mostly quoting people like Nathan Roth and Dan Kaysen.
Hi, that was great. I had a question about your simulations because they're very beautiful.
Sure.
They only went to about 2 months, which is good. But have you considered, or rather, is it possible to go to like say 2-3 years after disruption? Yeah,
that's a very good question. I think with our existing code, no. But we have a variety of plans for algorithmic improvements that will let us go further. I would say that on the algorithm side, Elad has a number of ideas for improving some very technical things. Ultimately, the dominant component in our computational budget is actually building this unstructured Voronoi mesh, and there are realistic ways to speed that up. So I think from that we can maybe get a factor of 2 improvement in efficiency, but something that's maybe even more promising is the fact that we seem to be over-resolving the problem at late times. So very high amounts of resolution are needed at early times when you're simulating the extreme compression of returning debris streams. But after these streams just start blowing themselves up in shocks with the disk, our simulation is actually very well converged compared to test runs that have 5 times fewer resolution. So what we're hoping to do in the future is to sort of intelligently de-refine the simulation at late times once we no longer need to really resolve the stream dynamics. And I think that will let us improve our runtime by a factor of a few. So I think there's a factor of 2 here, a factor of 2 there. We can probably get out to maybe 5 or 6 months in the next round. That's what I'm optimistically hoping.
Hi, yeah, thanks for a great talk. You mentioned that we're planning to expand the hydro simulations into parameter estimation, parameter space exploration. If you would have to guess on your intuition now, what do you think would be the most important parameters? And out of personal interest, I don't think you talked about this, but does the stellar structure at all come into play for the expected photometry?
Great questions. So I'll answer the second one first because my answer is very simple. I can just point to Jamie Law-Smith in the audience, who is the world expert on how stellar structure affects the evolution of a TDE. From my perspective, what I would say is that when the star is destroyed, you wind up with some frozen-in spread in debris energy, so the amount of mass per bin of orbital energy, which sets the rate of mass return to pericenter at later times. And the internal structure of the star is encoded in that mass fallback rate. Now, the degree to which this affects things, my understanding is that for main sequence stars that are really not on the terminal age main sequence, and if you're talking about full disruptions, the effect is generally minor at less than the factor of 2 level. But once you start talking about very weak partial disruptions or stars at the very end of their main sequence lives, it can become a more dramatic effect. Now, with regards to your first question, okay, that's a good one. From just a purely personal level, what I would be the most interested to see is TDEs with more relativistic pericenters and very misaligned orbits. Because what can in principle happen there is that lens-Thirring precession from a misaligned black hole spin vector can cause streams to totally miss each other and to wind up into a more complicated three-dimensional structure. So this, I think, may be a very interesting way for the spin of the black hole to be imprinted on the optical UV light curve. So that's one thing I'm very excited to look at in the future.
Please.
Yeah, very fantastic talking about. So I was wondering, have you also thought about some follow-ups of radio? It was fantastic that you had this optical UV and X-ray, but we had a very talented graduate student, is now a postdoc, Brandon Kerr, that he did a very great job at saying, simulations, and we figured out that we can find them using the event horizon telescope and the next generation, up to 110 of the megaparsec. I wanted to know where your comments are, if I could talk to you or something.
Yeah. So radio emission from relativistic or subrelativistic outflows in TDEs is very interesting, and there are a ton of people at the CFA doing state-of-the-art work discovering new things about that. I guess from my perspective, one thing that I find very interesting is that when observers have taken late-time radio follow-up of thermally selected TDEs, ones found by either thermal optical or thermal X-ray emission, you often wind up just with upper limits. And when you find radio emission, it's often relatively weak. And you can sort of turn this around, and there are a few assumptions that go into it, but you can turn this around into a constraint on the jet launching fraction in tidal disruption events. It appears, I would say, that most TDEs are not launching off-axis jets. So even if a powerful jet were launched off-axis, at late enough times, once it had decelerated to transrelativistic speeds, it should make a quasi-isotropic radio afterglow, and this is not seen in the majority of thermally selected TDEs. And the reason this isn't seen, I think, gets to some very fundamental questions in jet launching physics. So superficially, it seems like the conditions, at least at early times in TDEs, are pretty appropriate for jet launching, in that the initial rate of mass fallback is often very super Eddington, and at least in X-ray binaries, super Eddington accretion is often associated with jet production. This is also seen in GRMHD simulations, for example, like Brandon's. So this suggests to me that there's some kind of hidden variable in the TDE problem, which is making TDEs bad at powering relativistic jets. This hidden variable might have to do with the unusual physics of a tilted accretion disk. So unlike most black hole accretion disks, TDE disks do start off tilted. It may have something to do with the net magnetic flux. So there are other reasons to suspect that maybe TDEs are kind of magnetically starved accretion disks, and maybe you don't have enough colloidal magnetic flux to power a very strong relativistic jet. It might be something else entirely. But I think the unknown answer to this question is something that makes me scratch my head, and I would really love to know the answer.
One thing like that, also the population of TDEs that we just discovered, they were not too much super Eddington. And it turns out that there is a rapid time evolution for them. So maybe we were not lucky enough to observe them during the time that they were super Eddington. So hopefully LSST or your instrument will help us out to increase this.
That's actually not the case.
Oh.
We observed them in the radio from early time, during the super Eddington phase, and then many years later. Yeah.
But I think that does get at one other possible explanation, which is maybe contrary to what I showed you in these simulations. I don't know, maybe there was a bug in the code, and maybe this runaway circularization doesn't happen. You could imagine that if circularization is always very inefficient, then a super Eddington rate of mass fallback is not translated into a super Eddington rate of disk accretion. So if you don't believe what I showed you in the simulations, and of course you should always be skeptical, then this might be another way to suppress jet formation.
Okay, we're at 5 minutes after the time, so I'm going to ask any last questions to come on up, and let's thank Nick once more.
Thanks.
Very nice.
Oh, thank you so much.
I'll see you.
Yeah.